A very good evening, everyone. We are from Group 14, and today we will present our case study on the design and engineering challenges of the AeroHeart magnetically levitated left ventricular assist device, which is LVAD. So let me start with a small introduction. So basically, heart failure happens when the heart cannot pump blood effectively. Because of the donor hearts are limited, LVADs are designed and used to help patients with severe heart failure. However, the conventional LVADs may cause blood clots, which is thrombosis, blood cell damage, hemolysis, and also mechanical wear from bearing. To overcome all these problems, AeroHeart developed a centrifugal LVAD with magnetic levitations, or what we call is maglev technology. So this design is basically used to reduce the frictions and improve blood compatibility. So in this case study, our system aims to improve durability, energy efficiency, and also the patient safety. So next, we will explain the design challenges and also the performance of the AeroHeart LVAD.
Hi, my name is Nurin Elisa binti Marcharia, and I will explain to you about the design architecture and checks-off of the LVAD. So the team selected the centrifugal continuous flow pump because this design provides the better hemocompatibility and long-term reliability compared to the older pulsatile pump. So centrifugal pumps are more smaller, quieter, and contain fewer moving parts, which helps to reduce the mechanical work and maintenance issue. In this pump, the blood enters the center of the impeller and is accelerated radially upward to produce continuous blood flow. So one of the major advantage of this centrifugal design is that it operates lower rotational speeds, and this helps to reduce the shear stress on the blood cells, which lowers the risk of the hemolysis and the thrombosis. In addition, the wider blood flow pathway reduces the blood stagnation and improve overall hemocompatibility. So the group also used the full magnetic levitation or maglev technology. In this system, conventional mechanical bearings are replaced by the magnetic suspension. The impeller remains suspended without the physical contact with the pump housing. As the result, the friction and mechanical work were greatly reduced. So maglev technology also creates larger clearance around the impeller, which improve the blood flow and minimize the blood damage. Other important benefits include reduced blood stagnation, lower thrombosis risk, reduced hemolysis, and improved durability. However, if the design priority changes toward the pediatric patients, the engineering approach must be considered. Pediatric patients have much smaller anatomical space, so the ultra miniaturizations become the main design constraint. Under this condition, an axial flow pump may become the better options because the axial pump are smaller and more compact than the centrifugal pump. So this allows easy implantation in the pediatric patient. So, however, axial flow pump also introduce several disadvantages. They require higher rotational speed, which increase the shear stress and may increase the risk of hemolysis and thrombosis. So the levitation strategy must be also re-evaluated for the pediatric patients. Full active maglev system provide excellent rotor stabilization and hemocompatibility, but they require Hall effect sensor, electromagnet, controller, and continuous power supply. This increase system complexity, power consumption, and implantation volume. Therefore, alternative suspension systems such as passive magnetic bearing or hydrodynamic bearing may be more practical for pediatric LVAD because they are smaller and simpler. However, the system may not provide the same level of the stability and blood compatibility compared to the full maglev technology. But overall, the engineering trade-off involves balancing several important factors, including hemocompatibility, device size, durability, power consumption, and the implantable feasibility. So, in conclusion, the centrifugal full maglev LVAD is more suitable for the adult patient, where the compact axial flow pump with simplified bearing system may be more practical for pediatric patients.
Good day everyone, my name is Pupuying and today I will in charge of explanation the part 3.0 which is the risk analysis and FMEA overview. So moving into the safety profile of the Aeroheart, our team conducted a comprehensive risk analysis. As we transition from the second generation mechanical bearings to the third generation full maglev technology, we essentially trade the physical wear for the electronic dependency. The primary engineering benefit here is the elimination of the friction, which extends the device's operational life to an impressive 10 to 15 years. However, this shift introduced a critical risk, which is a rotor crash. Because the impeller is suspended entirely by a magnetic field, so any loss of the electronic stability or the real-time feedback could cause the rotor is physically strip the housing. So clinically, this is terrible. It doesn't just stop the pump, it will cause the hemolysis happen or the rapid destruction of the red blood cell due to the mechanical impact. First, 3.1 power failure and redundancy. The first critical challenge we address is power. A MATLAB system is active, meaning it requires a continuous high frequency current to keep that rotor center thousands of times per second. So to mitigate the risk of a sudden power cut, we have employed a dual redundant battery architecture. We use two independent external Leon packs. If one fails or is disconnected for a swap, the second battery instantly assumes the full load with zero drop in pump speed. So for our worst case, which is the total power loss, we have integrated an internal emergency capacitor which is directly into the controller. So this acts as a high-speed reservoir, providing a vital safety window. This can ensure enough time for the patient to reattach a lead or for the system to execute a control spin down, which preventing a high impact mechanical crash. 3.2 Sensor failure and TMR. Next, we look at the eyes of the system, the Hall effect sensors. These sensors monitor the rotor's position in real time. If a sensor drifts or fails, the magnet could accidentally pull the rotor into the wall, leading to thrombosis or clotting happen. So our solution is triple modular redundancy or TMR. As shown in figure 1, we run the three identical systems in parallel. We use a majority voting logic circuit. If one sensor starts providing the faulty data, the system identifies it as an outlier and ignores it. This ensures the impeller remains perfectly centered based on the two healthy signals, maintaining the mandatory safety limits required for the rotary pumps without any interruption to the patient's blood flow. 3.3 External electromagnetic interference EMI. Finally, we address the environmental risk. Third generation VADs are highly susceptible to external EMI from sources like airport scanners or industrial motors, which can discouple the magnetic bond of the rotor. Our defense is twofold. First, a hardware defense. The pump housing is lined with the mu metal shielding, a specialized alloy that redirects the magnetic flux away from the levitation components. Second, a software defense based on the IEC 62304 standards. The software acts as the brain. If it detects a displacement caused by the EMI, it triggers an automatic recovery protocol, which is an instantaneous high torque pulse to snap the rotor back to the center. If the interference is too severe, the system reverts to a default mode, maintaining a constant safe speed. Combined, these hardware and software redundancies move Arrowheart from a benchtop prototype to a validated, life-saving clinical solution.
Okay, next I will explain about the adaptive control system for the Arrowhead LVAD. Basically, the problem with a fixed speed LVAD is that runs at one constant speed all the time. It doesn't change based on what the patient doing, but our body, the heart, naturally adjusts blood flow depending on activity. For example, when a person resting, the body is usually needs
usually needs about 5 liters of blood per minute. But during exercise or any physical activity, our body needs 15 or up to 20 liters per minute. So if the LVAD stay at the same speed, it may not meet the body actual needs. So this can cause some problem during exercise. The pump may not supply enough blood, so the body may not get enough oxygen. At the same time, during rest, the pump might work too strongly, which can over unload the ventricle. In some cases, this may even cause suction events, where the ventricle wall is pulled inward, and that can affect stability. So, because of this issue, adaptive control system is introduced. The main idea is to make the LVAD smarter instead of running at one fixed speed. The pump can automatically adjust according to the patient condition. For the example, when the patient is active, the pump can increase its speed. But when the patient is ready, it can slow down. This help the device respond better to physiological demands and make it closer to how a natural heart works. So overall, adaptive control is important because it can improve safety, reduce complication, and provide better support for the patient in daily activity. Okay, next I will explain the sensor integration strategy used in the adaptive control system for the Arrowhead LVAD to make the LVAD respond according to the patient's condition. Several sensors are integrated to monitor physiological change in the real time. Each sensor provide different information, and together they help the system decide the appropriate pump speed. Okay, we go. The first sensor is the accelerometer. This sensor detect physical movement or activity. So when the patients start walking or exercise, it can detect the increased motion or signal that body may need more blood flow. The second sensor is the heart rate sensor. This monitor change in heart rate. Usually, when the body needs more oxygen, such as during exercise, the heart rate increase. So the sensor help confirm that the physiological demand is actually increasing. The third one is the left ventricle pressure sensor. This is important because it's a measure preload, which means the amount of blood filling the ventricle before pumping. If the preload becomes too low, there is risk of suction or ventricle collapse. So this sensor help prevent that by allowing the system to adjust the pump speed safely. Next is the flow sensor. This sensor measure the actual blood flow produced by the pump in the real time. It ensures that the output matches what the body needs at the moment. Lastly, the SVO2 sensor measure oxygen balance in the blood. So during exercise, oxygen demand increase. So this sensor helps detect whether the body require more circulatory support. So, overall, by combining these sensors, the LVAD can be better understand the patient activity level and physiological condition. This allow the adaptive control system to adjust pump performance more accurately and provide safer support that is closer to natural heart rate.
Alright, now for my part, I'm gonna explain about the verifications and validations. As we know, before a medical device such as an LVAD and such as the LVAD we use for humans, we need to pass through the strict regulation process to ensure that the device is safe, reliable, and effective. So, two important key, two important key, which is the verifications and validations. First of all, is verification. We need to checking whether the device is built correctly according to the design specifications or not. Then the second one is validations. We need to check with whether the final device is actually meets the user and the clinical needs or not. Alright, so first of all, as you can see, is preclinical testings. We do the animal studies are conducted. As an example, the LVAD may be implanted in animals such as sheep or pig because their cardiovascular system is similar to human's body. From this, we can observe that we can observe the blood circulation performance, heart support capability, risk of blood clot formations, and any tissue damage or infections. And next, about the biocompatibility. Um, all the materials used need to have the biocompatibility testing, such as if the um, as the analogy, if the pump material reacts negatively with blood, it may cause clotting or destructions of red blood cell. Therefore, materials such as titanium or medical grade polymers are commonly used because they are compatible with the human body. This process is to validate that the material are safe for the patient's use. Next, we continue to the reliability. Reliability is we need to do the durability testing. For example, an LVAD may need to run continuously for several months or even years um, to detect failures. So the engineers need to perform the continuous operation test, stress testing, battery endurance testing, mechanical wear analysis, so that this can ensure this device it remains functionally even during long-term use. And then about the software safety. Because we know if the blood flow suddenly drops, the software should automatically adjust the pump speed to maintain the proper circulations. Or in another example, if the sensor failure occurs, the system should trigger an alarm so that the patients or the doctor can alert with the situations, so can have immediate actions. That's why the software safety is very important. Then next is and the last one, the very important one is the clinical approval. Comprehensive validations and regulatory review are required before the device can proceed to the human use. The device needs to have the approval from FDA or Medical Device Authority (MDA). This will review they will review safety data, test results, device performance, and risk analysis. And this is the also for this is also for gain the trust from the user. Um, Lastly, if the LVAD successfully pass all these laboratory and animal testing stages, this can move to clinical trials and that involving human patient under strict medical supervisions and ready to sell and to market, to put and to have a place in the market. That's all from me.
So, in conclusion, the AeroHeart MagLab LVAD has shows a great potential in helping patients with advanced heart failure. So, compared to conventional LVADs, our design priorities the safety of patients with more efficient because The full magnetic levitation system helped to reduce frictions, blood clot formations, and also the blood cell damage. So throughout our case study, we can see how biomedical engineering like us on control system and safety design all work together to improve the patient care and device performance. Even though there are still challenges like miniaturizations, reliability, and clinical testing, the AeroHeart system is a very promising technology for future cardiac treatment. So overall, I hope our case study has shows how engineering like all of us here shows that innovations can improve and contribute to developing smarter and safer medical devices for healthcare. That's all for our group presentations, and thank you.